SAS Demonstration, Statistical Tests, Part 2. The data set that we are going to be using for this demonstration comes from research by Afifi and Azin in 1972. Data was collected for 113 patients at the Los Angeles County Hospital Shock Unit. For each patient, data was taken on admission and either shortly before death or before discharge. The patient's survival status was also noted. The raw data for this study are contained in the file afifi.dat, and there are 2 lines of data for each person in the study. So you see here in our input statement, we have a number 1 and a number 2 indicating that there are 2 lines of data for each observation that's read in. And we're reading in the ID number, the age of each patient, gender, their survival status, what type of shock they experienced, their systolic blood pressure at time 1, their mean arterial pressure at time 1, their heart rate at time 1, a cardiac index at time 1, their urinary output at time 1, and their hemoglobin at time 1. And from the second line per observation, we're reading in the time 2 measurements. And then in the data step, I'm creating a categorical variable for shock. So I'm saying that if shock type equals 2, and 2 represents no shock, then shock equals 1. And if shock type are any of these values 3 through 7, then shock equals 2. Just so you know what each level of shock represents, 2 stands for non-shock, 3 stands for hypovolemic shock, 4 stands for cardiogenic shock, 5 stands for bacterial shock, 6 stands for neurogenic shock, and 7 stands for some other kind of shock. So this is the format codes that we're going to be using with our data. So the first thing I'm going to do is just print out the first 10 cases and also look at descriptive statistics of the continuous variables. So here is the printout of the first 10 cases in our data set. And you see that we have attached formats, and notice I've done something a little bit different with the formats. I actually created the formats to include what the code number was as well as the format. So I actually made a format that was 2:female, 3:died. And then we have all of our lab measurements that were taken both at time 1 and time 2. We have whether or not the patient died, whether or not the patient experienced shock, and we also took a difference between systolic blood pressure between time 2 and time 1. If we look down here, we see we have our descriptive statistics for all of the continuous measurements, and notice that for most of the measurements we do have complete data. So the first statistical procedure we're going to look at is PROC-core, where we can have SAS produce correlation coefficients. And so we're interested in producing a correlation matrix of systolic blood pressure at time 2, the cardiac index at time 1, heart rate at time 1, hemoglobin at time 1, and mean arterial pressure at time 1. And we're not changing any of the defaults. So let's take a look at what this output looks like. Here we see the full output from PROC-core. So first of all, we start out by just seeing some simple statistics on the variables that were included in the procedure. So we have the number, the mean, standard deviation, sum, minimum, maximum, and the label. And then we see that by default, SAS gives us the Pearson correlation coefficients. And notice that we have here, our first row is the actual Pearson correlation coefficient. So if we go over to look at the mean arterial pressure at time 1, we are looking at the correlation between the mean arterial pressure at time 1 and systolic blood pressure at time 2. And the correlation coefficient is about 0.42. The p-value, less than 0.0001, indicates that this is a statistically significant correlation coefficient, where we're testing the null hypothesis that the correlation coefficient differs from 0. And then finally, the n that was used was 113. By default, when we're doing proc-core, we do pairwise deletion, which means that the number of subjects that are included in an analysis depends on whether that subject has data for both of the variables that are being correlated. So here, when we're correlating cardiac index at time 1 and systolic blood pressure at time 2, only 110 observations had complete data for those two variables. However, when we look at the heart rate at time 1 and systolic blood pressure at time 2, we see that all 113 patients had complete data for those two variables. One of the assumptions to do proc-core with a Pearson correlation coefficient is that both variables are normally distributed. So if we're interested in correlating systolic blood pressure at time 2 with cardiac index at time 1, we are assuming that each of those variables are normally distributed. Now, let's say we're concerned that we do not have normality of one or both of the variables. Then the non-parametric method for producing a correlation coefficient is using Spearman's correlation coefficient. And so here, to request Spearman, we just write in Spearman in our proc-core statement. And the other thing I'm doing is I'm putting in this option no miss. And what no miss does is it does what we call list-wise deletion, which means that it excludes all observations that are missing values on any of these variables, so that in our output we will only see those observations that have complete data on all of these variables. Let's take a look at the output where we request the Spearman correlation coefficient and we want complete data on all of the variables, so only include observations that have complete data. So here we see that we're only looking at 110 observations. And notice here that instead of printing the sample size, the mean, standard deviation, sum, minimum, and maximum, like we saw when we ran proc-core before, because we're doing the Spearman correlation, we're getting the median, minimum, and maximum. So we're getting slightly different simple statistics. Also, notice here that we have, it's listed the Spearman correlation coefficient. And notice that we don't have a separate row for the n, because we know that our n is 110 for all of these correlations. So here, using the Spearman correlation coefficient, the correlation between systolic blood pressure at time 2 and mean arterial pressure at time 1 is again about 0.4 and is highly significant. The other thing I want to point out about this code that differs from when I did proc-core with the Pearson correlation coefficient is that when I have just a var statement, it does a full correlation matrix. It correlates every one of these variables with each other. If we have a var statement and then a separate with statement, in this situation, we're only going to have correlations between cardiac index at time 1 and systolic blood pressure at time 2, heart rate at time 1 and systolic blood pressure at time 2. So we're not seeing a full correlation matrix. And you can see this again in the output. We're only interested in correlating these time 1 variables with this one time 2 variable, systolic blood pressure. Let's say we were interested in doing a regression where we wanted to look at whether the mean arterial pressure at time 1 is predictive of systolic blood pressure at time 2. So to do a regression analysis, and here we're also asking for some diagnostics that I will go over, we're going to say proc-reg, and then we have a model statement, and our response variable goes first, followed by an equal sign, and then our independent variable or predictor variable, mean arterial pressure at time 1. And then I'm interested in doing a plot of the residuals by both the predicted values and the mean arterial pressure at time 1, or our predictor variable. And I'm requesting symbols with asterisks. And then I'm also creating an output data set called regdat, and what I'm outputting are my predicted values and my residual values. So let's take a look at what happens when we run this code here. So here is the output that comes from procreg. And we see that the p-value in the ANOVA table tells us if there is a significant linear regression. And in this example, we do have a significant linear regression because p is less than 0.001. The R-square tells us how much of the variance of the dependent variable can be explained by the independent variable. In this case, we have an R-square of 0.17, and this means that about 17% of the variance in time 2 systolic blood pressure can be explained by differences in mean arterial pressure at time 1. There's also an adjusted R-square, and that's not that important when we're doing a simple linear regression. An adjusted R-square is more helpful when we're looking at a number of predictors in the model, when we're doing multiple regression. And basically, the adjusted R-square imposes a penalty for having redundant or unnecessary independent variables. And actually, the adjusted R-square value will reach a maximum and then decline as additional non-statistically significant variables are entered into the model. But again, we're not focusing on multiple linear regression in this class, but I wanted to point out what the adjusted R-square was and where it is in the output. And then here are our parameter estimates. And the parameter estimates give us the information we need to determine the equation of the regression line. So our regression equation could be read as the predicted systolic blood pressure at time 2 equals 59.31, which is our intercept, plus 0.70, which is our slope, times the mean arterial pressure at time 1. Or we could say that for every 1 millimeter of mercury increase in the mean arterial pressure at time 1, the expected increase in systolic blood pressure is 0.70 millimeters of mercury. If we were to interpret the intercept, it is the expected value of systolic blood pressure at time 2 when the mean arterial pressure at time 1 is 0. And this is usually not of biological interest. Since this is a video, I thought it might also be easier if I put in the comment the interpretation of the regression output. So I've provided the equation of the regression line as well as my interpretation of the R-square. Now there are 4 assumptions to do a regression model. The first assumption is that the values of the dependent variable y have a normal distribution for each value of the independent variable x. Secondly, the variability of y is the same for each value of x. Thirdly, the relationship between the two variables is linear. And finally, the data are independent, and we know that by the study design. So the graphs that were produced by procreg are going to check for the linearity and constant variance assumptions. So here we have the regression analysis diagnostic plots looking at the predicted value against the residual and then the mean arterial pressure at time 1 versus the residual. So either of these plots can be used to check the linearity and constant variance assumptions. So in terms of equal variance, we're interested in whether the width of the point scatter is constant across values of our covariate. So if we look here, it appears that the width of these points are constant. We don't see any kind of pattern here, so we could conclude that the equal variance assumption has been met. And then in terms of looking at linearity, we're interested in whether there appears to be a random scatter of points about the y equals 0 line. So there's no obvious pattern. So again, it appears that our linearity assumption is met. So again, for equal variance, we're interested in the width of the points. And for linearity, we're interested in whether there's a random pattern around the y=0 line. So based on these diagnostic plots, the linearity assumption and the equal variance assumptions are met. We still have to check on the normality assumption, and we're going to do that by using the output data set regdat, and we are going to first of all do a histogram of the residual, and then we're going to do a normal probability plot of the residual. So here, if we look at this histogram of the residuals, it certainly appears that it's normally distributed. And then if we look at the normal probability plot, we don't see any departures from normality. So we can conclude that the normality assumption is also met. And by the design of the study, we assume that the data are independent. And finally, I'm showing here a plot of the mean arterial pressure at time 1 and systolic blood pressure at time 2 with a linear regression line. So once we've done our regression analysis and we've checked the assumptions, then I just want to do a picture of what this regression line looks like with our data. So here is a plot of the mean arterial pressure at time 1 with the systolic blood pressure at time 2 on our y-axis and our regression line plotted on the data. A couple of things I want to point out about this plot is that notice I have the interpol equal to RL for regression line, and we looked a little bit at this when we did graphing earlier in the class. And then we have our plot statement with systolic blood pressure time 2 plotted on the y-axis and mean arterial pressure time 1 on the x-axis. And then we've attached our axis 1 and axis 2 definitions to the vertical axis and the horizontal axis. So our symbol statement was used to put the regression line onto the plot. Now let's say we were interested in comparing the mean systolic blood pressure at time 1 between the shock groups. Now recall we have 6 different shock groups that we're interested in comparing the mean systolic blood pressure at time 1. And so we're going to want to do a one-way analysis of variance for this comparison because we have more than 2 groups. And then what I'm also doing is I'm going to be outputting the residuals so that I can do diagnostics on this analysis. So to do a one-way analysis of variance, we're going to use proc-GLM. And we have a class statement which indicates our categorical or grouping variable. And this class statement is very similar to what we saw when we did a proc-t-test, where we put the variable that indicated 2 groups as our class statement with proc-t-test. But instead of having a var statement, we're going to have a model statement similar to proc-reg, and we're going to have model systolic blood pressure at time 1, so that's our continuous variable, equals, and then our categorical or class variable listed. And then we're going to create an output data set called ANOVA DAT, and specifically we want to output the predicted values and the residual values. So let's run this code and see what the output looks like for this one-way analysis of variance. We start out with just some information on our variable. We see that shock type has 6 levels, and SAS lists the values of those levels. SAS tells us how many observations were read in and how many observations were used for the analysis. So 2 of our patients were either missing on the variable shock type or systolic blood pressure at time 1. And then if we scroll down, we see here that SAS produces 2 types of sums of squares, a type 1 sum of squares and a type 3 sum of squares. If you are doing a one-way ANOVA, then the type 1 and type 3 sums of squares are the same. If you are doing a model with multiple covariates, then the way it works is that type 1 sums of squares adjust for the previous variables entered into the model, and the type 3 sums of squares adjust for everything in the model at the same time. in general, I always look at the type 3 sums of squares when I'm doing a model with multiple covariates. So here we see our p-value being less than 0.0001, so we conclude that at least 2 of the groups differ in terms of the mean systolic blood pressure at time 1. And that's our conclusion. So we don't know which 2 shock groups differ. We only know that the mean systolic blood pressure at time 1 differs between at least 2 of the groups. Now the assumptions for ANOVA are similar to the assumptions for regression. We're interested in the normality of response. We're interested in the equal variance of the response across the groups. We're interested in whether the responses are independent and whether there's model linearity. Unlike PROC-REG, PROC-GLM does not produce residual plots for you. So here I'm making use of my output data set called ANOVA-DAT, and first of all I'm going to look at the normality of the residuals with a PROC univariate, as I did with PROC-REG. So here we're looking at the histogram of the residuals, and then we're looking at the normal probability plot. And based on both the histogram and the normal probability plot, we see that the distribution of the residuals appears normal. Then to check for linearity and constant variance, I'm going to use PROC-Gplot and do a plot of the residual on the y-axis and the predicted on the x-axis. So I'm again going to use this output data set, ANOVA-DAT. For equal variance, we're interested in the vertical spread. Are the bandwidths equal? Do they appear equal? And then for linearity, we're interested in whether there's some kind of distinct pattern. Is there equal scatter around the y equals 0 line? Does it appear to be increasing or decreasing? And based on these diagnostic plots, I would say that the equal variance and linearity assumptions appear to be met. Now, as I said before, when the ANOVA model is statistically significant, that just tells us that there is a difference in at least 2 of the groups. So in order to determine which groups are different from each other, we need to do some kind of multiple comparison. So here I'm showing you the 2-key method for doing all pairwise comparisons. And to do multiple comparisons in SAS, we have a mean statement in our PROC-GLM procedure, and we list our categorical variable shock type with a slash and then the particular test that we're interested in. So here we're interested in doing 2-keys test. So let's run this and take a look at the comparison of the mean systolic blood pressure, all pairwise comparisons. Okay, so here let's go back and look at the code. So we start with our class level information. Then we have our ANOVA table and our results here. And then we see the results of the 2-key multiple comparison. And so what it's telling us is that any comparisons that are significant at the 0.05 level are indicated by these 3 asterisks. So specifically, we see that non-shock group differs from the cardiogenic group. So when we're comparing systolic blood pressure at time 1 between patients who had cardiogenic shock versus patients who did not experience shock, there's a significant difference. Between patients who had neurogenic shock compared to patients that did not experience shock, there's a significant difference. And similarly, for bacterial shock, hypovolemic shock, and then we see a repeat of the same comparisons. So it kind of gives you the comparison where it says non-shock versus other, and then it reverses the comparison. But there are only 4 significant comparisons. And these comparisons are significant after controlling for the type 1 experiment-wise error rate. So we've adjusted for multiple comparisons with this 2-key procedure. And there are many other methods that we can request in the mean statement. So we could do a Bonferroni comparison as another example. Let's say we were interested in doing a multiple comparison method that compared all of our categories to one category. So in this case, let's say we were interested in, instead of doing all possible pairwise comparisons, just comparing all of the shock groups to the non-shock group. Dunnett's test is useful for that. Again, the problem is if you're doing many comparisons, as we did when we did the two-key method, which does all pairwise comparisons, it's more difficult to see a significant difference between the groups because we're doing so many comparisons and the p-value needs to be adjusted for all of those comparisons. With Dunnett's test, we're actually only going to do 5 comparisons because we're going to compare each of the 5 shock groups with the non-shock group. And let's see how those results turn out. So here is the one-way analysis of variance with Dunnett's test for comparing treatment to control. So again, the ANOVA table looks exactly the same. The difference is the type of pairwise comparisons we've requested. So here we only see 5 comparisons because we're only interested in comparing each of the shock groups with the non-shock group. And we see that those comparisons, with the exception of the subjects who had some other kind of shock versus non-shock, that's the only comparison that was not statistically significantly different. And just paging up, you'll see that when we did the two-key procedure, we have many comparisons that were done. So I want to point out that two-key is doing all pairwise comparisons. Dunnett's test is only doing 5 comparisons. Now sometimes you're not interested in doing all pairwise comparisons. Sometimes you may have planned or a priori comparisons that you want to do. And so you can actually write your own comparisons with a contrast statement. And I've given some examples of contrast statements in this bit of code here that I'm showing you. The thing I want to point out is that when you write your own contrast statements, they are not protected against type 1 errors. So you will have to do some kind of adjustment. And also, it's a little tricky to write these contrast statements. So basically, how you're writing them, you start with the word contrast. It's a contrast statement. And then you give a label for what type of contrast you want to do. And then the particular variable that which is the categorical variable that you want to do contrasts. And then you have a coefficient for each of the groups. So we have here 6 groups. The order of the coefficients must match the alphanumeric order of the class variable if it's not formatted. And the sum of the coefficients must equal 0. A 0 coefficient means don't include the corresponding level in the comparison. And levels with negative coefficients are compared to levels with positive coefficients. So if we're interested in comparing hypovolemic versus non-shock. Non-shock was the first group that was read in. And so in each of these contrast statements, you'll see that it always starts with -1 because we're interested in comparing the other shock groups with the non-shock group. So here we're interested in comparing hypovolemic versus non-shock. So hypovolemic is the second level of the shock variable. Cardiogenic is the third level of the shock variable. Bacterial is the 4th level of the shock variable. Neurogenic is the 5th level of the shock variable, and other is the 6th level of the shock variable. So basically, I've written out the pairwise comparisons that were done when we used Dunnett's test. And in this last contrast statement, I'm actually interested in combining those subjects who either had hypovolemic, cardiac, bacterial, or neurogenic compared to the non-shock group. So here I have the non-shock group being -4, and then I want to include all of these other variables except for the subjects who experienced some other kind of shock than the 4 I've listed. So again, I've actually written out my own contrast statements. These have not been adjusted, but what's nice about it is that, let's say you're interested in only one particular comparison, you can actually write the contrast statement yourself. So let's take a look at the output when we've written these individual contrast statements. So here, what we see when we've written our own contrast statements is we see this heading, contrast, and it actually lists those headings that I wrote, hypovolemic versus non-shock, and we have the p-value for this comparison. Again, this p-value has not been adjusted for the fact that we've done several comparisons. And then here is the comparison of cardiogenic versus non-shock, bacterial versus non-shock. So we see each of the p-values for these exact comparisons between these two groups. And finally, this is the comparison where if we had lumped all the patients together who had hypovolemic, cardiac, bacterial, or neurogenic, and compared them to the patients that did not experience shock, and we see that there's a highly significant difference in the mean systolic blood pressure at time 1. It is very challenging to write these contrast statements. One needs to think carefully about how you want to arrange the order of the coefficients in these contrast statements to make sure that you're doing them correctly. Another way of writing contrast statements is with an estimate statement. So this is very similar to what we did with our contrast statements, except that we're using the word estimate as the key word to start the statement. And basically the difference is that when you use the estimate statement produces an estimated mean difference, standard error, and t-test associated with the probability value instead of the f-test that was generated by the contrast statement. So again, these statements are very similar to what I wrote up here. Let's just take a look at the output and I will point out the differences. So differences here, we have an actual estimate of the mean difference between these two groups in systolic blood pressure at time 1. We have a t-value, and then we have the p-value. When we did contrast statements, we do not have an estimate of the mean difference. The p-values are the same. It's based on an f-test as opposed to a t-test. Now let's say that we were concerned about our assumptions for the analysis of variance. And we felt that our assumptions were not met, and so we needed to do a non-parametric test instead. The Kruskal-Wallis test is a non-parametric alternative to analysis of variance. So to do the Kruskal-Wallis test, we're going to again make use of the procedure NPAR one way that we looked at when we did statistical testing part 1. And again, we use the option Wilcoxon. And we have our class statement shock type and our variable systolic blood pressure time 1. Since there are more than 2 groups, NPAR one way will produce a Kruskal-Wallis test. So let's look at the results from NPAR one way. And so here we see the results from NPAR one way and the p-value from the Kruskal-Wallis test. So based on this p-value, we are going to conclude that the median systolic blood pressure at time 1 differs significantly between at least 2 of the groups. So when we want to do a non-parametric comparison of more than 2 groups, how do we do pairwise comparisons if the overall comparison is statistically significant? To do that, there's not a lovely procedure like ProcGLM has where we can just request all pairwise comparisons. What we need to do is we need to make use of the where statement for the pairwise comparisons, and then the p-values are unadjusted, so they need to be adjusted. For example, by multiplying the p-value by the number of comparisons that we're doing. So here, we found that there is a significant difference between at least 2 of the groups in terms of the median systolic blood pressure at time 1. Now we're going to do a pairwise comparison between the hypovolemic shock group and the non-shock group, and it's going to show an unadjusted p-value. So we're basically rerunning our NPAR one way, and we have a where statement where shock type equals 2 or shock type equals 3. And so here we've just limited to these two groups. We see that our p-value is 0.0003. We haven't adjusted it for multiple comparisons. But what we would want to do is, depending on how many comparisons we're interested in, we would have to continuously run this proc NPAR one way, selecting out the pairs of shock groups that we want to compare. So in this demonstration, we've looked at proc core, we've looked at proc reg, we've looked at proc GLM, and we've looked again at proc NPAR one way. This completes the SAS demonstration video, Statistical Testing Part 2.